All right, so I think we're ready to start with our first keynote. So maybe, Xin, if you want to install your laptop. So it's my honor to introduce Dr. Xin Tong as a partner research manager at Microsoft Research Asia and leader of the Internet Graphics Group. Can I take this for you guys? Yeah, I think it's going to be better. So Xin has made significant contributions to computer graphics and 3D vision. His research spans a variety of topics, including appearance modeling and rendering, texture synthesis, 3D learning, facial performance capture, and generation. Xin served as associate editor of top graphics journals like Tong and CGF, and now is the editor-in-chief of TVCG. So today, Xin brings us deep learning-based 3D understanding and generation, a cutting-edge exploration of the challenges and opportunities in addressing deep learning for 3D data. Please welcome Xin. Thank you.
Yeah, so thanks everyone for the kind introduction, and give me this chance to introduce our work on 3D deep learning. So actually, when I received this invitation, I actually feel a little bit upset to accept it, just because I guess most of graphics people regard me as a rendering guy instead of geometry guy. So I try to go back to my research life and try to find some evidence to show that I was actually a geometry guy. And I'm lucky just to find that when I started my research as a master's student, I started to construct some solid modeling system. And at that time, I tried to use some rule-based AI techniques for shape generation. Actually, I just tried to develop some algorithm to generate the chairs at that time. So I'm so lucky that after 30 years, I could start to work with my colleague, Yang Liu, Hao Pan, and other colleagues together to learn more geometry processing stuff and start my research work together on 3D learning and geometry processing again. So when I started my work on the data-driven geometry processing around 2016, at that time, the deep learning has started to demonstrate its advantage in many fields, such as image videos, audio processing, and synthesis, as well as NLP. So a natural question is that, can we use it on 3D graphics? So I think definitely the answer is yes. But we keep asking ourselves is that, what's the difference between 3D learning and the deep learning in other fields there? And over the years, we realized that the different from the other fields that our data is regular 1D or 2D samples that can be directly captured from the real world. And for the 3D shapes and its dynamics are really high dynamic, which high dimensional, which cannot be directly captured via the 2D imaging devices, or you can directly paint via the 2D interfaces. So this dimension gap leads to irregular and diverse 3D representations, and also makes the data is difficult to be captured, modeled, and labeled. So as a result, for 3D deep learning, we have to design a new deep learning framework for the irregular and diverse 3D representations. Since the labeling 3D data is so difficult, so the unsupervised or the weak supervised scheme are highly desired in 3D learning. Also, we need much more efforts to construct a scalable and generic deep learning solutions based on the relatively small amount of the 3D data we have in hand. So in the past years, our group have done a set of works on the 3D learning, and we focus on two directions, the 3D understanding and the 3D generation. So for the 3D understanding, we focus on exploring efficient network design and training schemes to support various 3D understanding tasks. For the 3D shape generation, we try to say whether we can develop some generic and controllable generative models to generate high-quality 3D shapes there. Yeah. So in the following part of this talk, I will introduce our work along these two directions. But due to time limit, I will mainly introduce the motivation and some key ideas of each work and share with you that what we have learned from these works there. Some published in the paper, but some failure cases not published in the paper. I'm sorry that I will not describe the technical details of these works and some related outstanding works done by other colleagues and researchers in this field. So let's start from the deep learning for 3D understanding. So in these directions, our basic idea is that we want to follow the advances of the deep learning paradigm in the vision and NLP field and try to adapt this new paradigm to the 3D deep learning. So as shown here, if you look at some paradigm shift in the NLP and vision field, they start to develop some dedicated neural networks for each specific task in the early stage. Later, since they have a lot of data, they have pre-trained some backbone models that can be used for different tasks after fine-tuning. After that, the unsupervised pre-training scheme has been developed so that the backbone model can be trained on a huge amount of unlabeled data layer. So after that, in the NLP domain, the GPT unifies the generation and understanding tasks in one unified model, and they try to train a large language model for all the different NLP tasks and follow this scaling law and got really, really great progress there. Yeah. So to follow this paradigm shift, we need to first develop an efficient deep learning framework to enable this 3D deep learning scenes. So in particular, we hope that this 3D deep neural network framework should support irregular and diverse 3D data as input. Also, the computation cost and the memory footprint of the network should be small so that the training and inference can be done efficiently on the GPU side. So to this end, our key idea is that we just follow the tradition in the graphics and use the octree data structure to regularize the input data into a regular grid on a sparse regular voxels layer so that we limit the network operations on these non-empty voxels so that the memory and computation cost could be the O(n) square, but not the O cubic layer. So we also designed some efficient hierarchical data storage scheme so that all the data access in the training and inference stage can be done very efficiently on the GPU side. So based on these ideas, we have developed a set of octree-based deep learning framework to support the convolutional neural networks, graph neural networks, as well as the transformers, and demonstrate their efficiency to the different deep 3D learning tasks. All these works have been published in SIGGRAPH, and we release our code model in the website. So what we have learned from this work? One interesting I want to mention here is that when we start this OCN work, octree-based works, we try to limit our computations on these sparse voxels only. At that time, I'm really puzzled. I'm wondering, does this work? If you only limit the convolution, full convolution, only on sparse voxels, whether we can learn something there. And our project means that it works. But later, we gradually found that those non-empty voxels actually still contribute something to this learning process. So later, in the dual octree process, we just include those empty voxels back in our whole learning process. We develop this adaptive frameworks layer so that you can both the empty voxels in the node in the upper level, and some irregular non-empty voxels can all contribute to this learning process. We get a better result. That's very interesting findings during this process. Another thing is that although we find the octree-based 3D learning framework is very powerful for 3D understanding, but the whole octree subdivisions actually is obtained from the input data layer. And when we want to use this for some generation process, it's so difficult for us to learn this subdivision scheme from the latent code or something like that. We try several times, we discuss a lot, but until now, we still cannot figure out an efficient scheme and try to learn this subdivision scheme from the data and use it for efficiently for the 3D generation. It's still an open problem, at least for us. And after we have this octree-based framework for 3D learning, we start to explore some pre-training model for the 3D understanding tasks. So the goal here is that to develop some backbone model and unsupervised pre-training scheme for 3D learning. We start from unsupervised 3D pre-training just because it's so difficult for us to obtain a huge amount of labeled data for this pre-training task. So specifically, we have a backbone model as a shape encoder, and we try to learn some shape features from a lot of unsupervised 3D data, unlabeled 3D data. So the backbone is trained with a large amount of unlabeled data. After that, we fine-tune the back-end model with a task-specific backend with the labeled data for each specific understanding tasks there. So you just follow the general paradigm in the vision field about this pre-trained model plus with the backend. So developer scheme for 3D learning, our key observation is that if you look at those different 3D understanding tasks, and we need both the features in the shape level, and we also need some features from point level there. And moreover, these two levels have some coherence, and we believe that we should learn it jointly together. So based on this key observation, we design an octree-based HRNet that can output multiple resolution features. This HRNet structures actually is widely used in the vision field also for tasks in different levels there. We leverage these data structures. And also we follow the contrastive learning approach in the vision field for unsupervised backbone training. To this end, we develop multiple resolution instant decreasing schemes to learn the shape level and point level feature jointly. So for shape level, we regard each shape as an instance, and this rotating version as a similar same samples, and all the other shapes as different samples. And for point level features, we just do some point clustering on each shape, and all the nearby points will be regarded as the same sample, and other patches will be regarded as different samples for this contrastive learning approach. And we validate and test our methods for different 3D understanding tasks, and we show that using this pre-trained model, after fine-tuning, our model can outperform to other existing models, especially when you have only a very, very small number of the labeled data for these tasks. So we are really happy that the whole framework works very well for the 3D understanding task as a backbone. But however, we also found that the computation to the model, compared to the model that is trained from scratch with that labeled data, the performance gain of the backbone model actually is somehow incremental. It's not so significant compared to the pre-trained model used in the 2D vision field. So I guess we try to analyze the reason. We found there are several possible reasons. Probably the network design is still not so powerful or not good. And also, if we compare the data used for training these backbone models, so the amount of data we use to train the backbone model is still relatively small. And also, when we try to improve our model and try to use more data, we found that the benchmark somehow we use there is based on the relatively small amount of the synthetic data. And even some simple approach can achieve relatively high score there. And to get this little bit more gain, performance gain of that, we need to really carefully fine-tune our model. In some sense, we feel that that benchmark may not be a good metric to verify us which backbone model is really good or not. Somehow the benchmark is overfitted somehow. That's our feeling. But we don't have proof, we don't have evidence there. So after that, we say how we can keep improving our backbone model. So we develop the third work we call Swing 3D here. So goal of this work to design a good backbone network, and we choose the indoor 3D scene understanding as our task due to several reasons. The motivation behind actually for us is that at that time, the transformer just show its really good performance in the vision and NLP field. Of course, in the NLP field, people use the transformer, but in the vision field at that time, people start to use the transformer and really show that it outperformed to the CNN. But when we say the existing works that try to use the transformer on 3D understanding tasks, we found that their performance actually is inferior to the CNN-based solutions, convolutional-based solutions. And we want to know that whether we could really develop a very efficient transformer models and beat the CNN models. And one thing we found that is that most likely we need more data to train the transformers so that we can get this benefit. And we focus on the 3D indoor scene understanding just because they have the benchmark, ScanNet benchmark really good based on the real data. And if you look at the best performance score there, it's still not good, which means the test is relatively difficult for all the models, still difficult for all the models. And also, we found some large-scale synthetic data, and it's 10 times larger than ScanNet, and it can be used to test our ideas and train these transformers there. So we want to answer the question is that if we use really much more data for training these models, can we scale up the performance as the model size increases and the data increases there? That's the question we ask ourselves. So our key idea is very simple, is that we adapt the state-of-the-art swim transform models at that time to the our 3D understanding tasks. And we pre-train our backbone on large synthetic data set. That is 10 times, we mentioned it's 10 times larger than ScanNet data. So after that, we just fine-tune our model on the real data, ScanNet data, and S3D data for a set of 3D segmentation and detection tasks and check their performance. So to train the backbone on larger data set, we try to develop efficient self-attention operators on these sparse voxels in 3D, which can change the time and memory complexity from ON squared to ON, which is really critical for us to train the large model on a very large data set. And also, we try to keep this network design as simple as possible, and we only add some new component when necessary, and we prove that it works on the large data. Otherwise, we just keep very basic network structures there. So we verify our model on the ScanNet and S3DS benchmarks. It shows that our method not only achieves the state-of-the-art results at that time, but also show that its performance could increase as we use the larger data for the backbone training. That's good things. And also, it's first time beats the CNN-based model for a lot of all the benchmarks there. That's a good sign there. So another good thing, actually, we learned this, is that it's the first time for us to try to train the model using synthetic data. And after that, we just fine-tune the model on the real data. If we compare the synthetic training data of the 3D data and compare with the real white noise data, the question actually we don't have answer is whether it works. So we tried and found that it works, and it was quite good. And let's give us a good, how can I say, evidence show that we can collect more synthetic data maybe, and train with the real data together and obtain the good performance for this backbone model trainings. And another thing we learned that during this project is that efficient implementation on the network is really critical if we really want to speed up the training process, especially when you want to train a larger model or train the model with a relatively large data set here. And another interesting thing is that we found that we try to test some neural network design, some improvements people mentioned or proposed in other works there on the transformer. And we found that when we increase the size of the data and the model in the training, and those tricks or improvements just lose their power. It's that when we have the more data, when we increase the size of the model, it seems that a simple model works quite well on it. On the negative side, we also realize that to train a good backbone model for the different 3D understanding tasks, we need to collect much more data here. And also seems that if you go back to say the performance increase there, it seems that when we add more and more data, the performance again there seems not good, right? It's become flat. We discussed with the vision guys, and we found that they suffer the same problems. Still, until now, today, they still solve these scalability problems. We find the same thing there is that when they increase the amount of data in the 2D vision tasks there, the performance is not increased as an NLP task there. They try to solve this. We suffer the same problem. Yeah. So in summary, we reviewed some explorations. Our explorations we have done to follow and adapt this paradigm shift of the deep learning in the vision and NLP field to 3D learning field there. So as shown here, if we believe that the way that the vision and NLP developed is the right way we should follow, I think we still have a long way to go here, and we still need to find a backbone model. All the people agree and will use it for different 3D understanding tasks, and develop very efficient and supervised pre-training schemes there. And later, its question is that how to unify this generation model and understanding model, and whether we should develop some new problem formulations, for example, based on the promote, to gather all the problem or tasks done in one unified framework. There's still a lot of open questions or problems here we need to work on. And in the vision field, I think they are still struggling and fight for these problems. Yeah. So now let's move to the 3D generation field. So in this field, I will also introduce a series of works. And the first work I will introduce here is SDF style GAN. So I think the name of the work clearly shows that the goal is that we want to develop a generative model for the high-quality 3D shape generations. And the idea here is very simple. It's that we want to adapt the style GAN that is very successful in the 2D face generation to the 3D shape generation. And moreover, we hope that we can get a really good W or W plus space as style GAN show in the face generations, so that we can get better control in the shape generation and some editing capabilities, just because we play some tricks in the W or W plus space. That's our motivation. To frankly to say, when we start this project, we are very curious that whether it's too straightforward, and if it works, why we haven't seen people try it before? What happened there? It's just because it's too simple, people tried, and people discussed it, but we look at all the existing work on 3D shape generation, it seems that its quality is not there. So as we start the exploration and train the models, we realize that we need to design some new discriminators in this task. As shown here, that for the shape generations, we found that the normal quality is really, really critical to determine the quality of the generated 3D shapes. And the second, we found that for a single discriminator cannot preserve both the large shape structures as well as the local shape features there. So we thus need to develop some two-scale discriminators in the GAN training there. So we just improve those schemes and got these gradient discriminators and two-scale discriminators there, and for the style GAN framework, and we train these style GAN shapes for 3D shapes. And you can see that compared to the previous approach, this SDF style GAN really improved the result quality of the 3D generations. And also, here you can see that we also preserve all the diversity of the generated shapes compared to the ground truth 3D shape set. So what I have learned is that we found that, this style GAN actually works for the 3D shapes. And it really creates some high-quality results there. And the training is relatively stable. And unfortunately, when we train this, we found that the W space and W plus space we learned for the shape generation actually is not so meaningful compared to the W space for the face generation. We don't know why, but just because, maybe because that the shape variations is too large. They have different variations about structures, details there. But anyway, and this W space, we try to do some interpolation or some navigation in W space. We found that it cannot be used for editing or some control purpose there, unfortunately. And also, when we try the GAN training, we found that the GAN training is only stable when we want to train the model for one specific category shapes there. When we want to train the GAN for multiple categories, it failed. And another additional thing we found that when we develop this algorithm and we try to evaluate their qualities, we found that some existing metrics people used to measure its generation qualities cannot well evaluate 3D generative models. And the score is not consistent with the human perceptions. Sometimes you'll find generate so bad results there, but the score is high. So that we just propose an image-based FID score in this work to evaluate the quality or diversity of generated 3D shapes, and we found that it's consistent to the human perceptions. Then we will try to use it later in our experiment, in our analysis. Yeah. So after this works, we start to seek for some generative method that can provide a better generality and controllability and develop LAS diffusion, so in the last year. So the goal of this work is to develop a generative model for the high-quality 3D shape generation. So we start our method, we want our method not only can be controlled by the users to generate shapes with the desired local structures, but also can generalize to other shape categories that are not in the training data set. That's our ambitions. So the key idea of our method is to train a diffusion-based 3D generator that can be controlled by the 2D sketches. And our key observation here is that the 2D sketch provide a good way for the 3D shape structures and control through the 3D structures. It can be easily drawn by a user, or you can extract it from the 2D image. Well, the 3D diffusion model can will produce all the shape details learned from the training data set. That's our basic idea. And also the diffusion model has proved that you can train a really diverse data set layer and learn the distribution layer and generate the shapes in the different categories layer. So based on this key idea, we developed a two-stage diffusion model for the high-quality 3D shape generation. So in the first stage, we used the occupancy diffusion model to learn to generate a low-resolution occupancy field of the 3D shapes. Then in the second stage, our SDF diffusion model will refine general occupancy field with a diffusion detail, SDF details layer to gather all the shape details layer. That's a two-step solutions. We also develop a view-aware local attention schemes that can project the input sketch to the generated shape volume so that the user can efficiently control the local shape structures, whereas the input sketches. For each sketch, locally, they will project to the surrounding voxels and do this attention. That's the basic idea. Yeah. So here we illustrate some 3D shapes generated by our approach. You can see that compared to the existing sketch-based 3D modeling method. So you can see that our method can, without any sketch input, our method can well reproduce all the detailed 3D shapes, structure variations for the different shape categories there. Yeah. So here we illustrate the 3D shapes generated by our approach, and using the given the different sketch, and we compare our method with the previous approach. You can see that our method can well follow the input sketch and generate all the structure details, and compare to the traditional approach, and also can generate really good 3D shapes and all the sharp features there. And we also test our method whether it have some generalities. And on the left side, we just draw some sketch and try to generate some models, and those shapes categories are not in our training data set at all, and we say whether we could generate those shapes. And it works somehow. And on the right side, and since we train our model using a sketch, automatically extract from image or 3D models. And here we just use some human hand-drawn sketch layer to check the robustness of our approach. And it works okay, not so good, but it still generates some reasonable shapes there. Yeah. So after we try this, we found that actually, when we start this project, we really have these high ambitions, is that we try to say, if we use a sketch, control the diffusion models, our initial thinking is that if we can use some image diffusion model to generate some image from text promote, and then we can extract the sketch from this image layer. And if the model works very well, we hope that we can generate arbitrary shapes from the image sketch extract from image input. That's our ambitions. So during the project, we try a lot of different schemes, try to achieve this. For example, we try to randomly combine the different shapes, and then we can generate some sketch there so that we hope that we can train the mapping between the sketch to arbitrary shapes here. And we believe that for the local shape details, we only needed a small amount of data so that we can learn there. But unfortunately, we tried different schemes. We found that it still doesn't work. It failed. And although we got this relatively good result, and as you can see in the last slides, the LS diffusion actually demonstrates some kind of generalities and to generate some reasonable shapes for unseen shapes. But those shapes is quite close to the shapes we have seen in the training data. And on the other hand, and when we try to give some sketch is far away from the training data or something like that, although the part of it have been seen in the training data, it still cannot generate shapes. Only a part will be seen and in the training data set. That's our initial goal, but we found that it fails. And it's still clear to me why the approach fails. And we found one possible reason is that we found the diffusion model might still not powerful enough. The reason we think about that is that we train the diffusion model on the when we train the model on the multiple category data, we found the FID score actually it degrades, which means we see the quality compared to the diffusion models we train on the single category. The shape quality actually degrade. We found, oh, probably the reason is that the base model is not powerful enough. We should try to gather really powerful base models. Then we try this idea and it may works. So after that, based on this feeling, we try to train a large diffusion model and hope it could achieve good performance there. And when we say this, we found that we still actually failed again. But the lucky thing is that during this process, we developed an efficient 3D decoder scheme for multiple view diffusion that is published in this year SIGGRAPH. So the goal of this work actually is that we develop a 3D reconstruction scheme for fusing the multiple view image generated by a multiple view diffusion method into a high quality 3D models. The very simple is that if you have the multiple view diffusion approach and you generate a multiple view of image of one object, you give the text promote or single image as a promote, and then our model will take all these multiple input and directly output as 3D models. And then we can also develop a texture mapping scheme, and we can map the textures into the model and generate the final texture mapped 3D models. So our basic idea here is that the multiple view diffusion models trained on large image generation models can provide good generalizability and controls to the users to create a multiple view image of diverse objects there. So, however, the views, if you look at those views generated by these multiple view diffusion models, it still cannot guarantee it's 3D consistent. So our approach is just to provide a very efficient 3D reconstruction scheme dedicated to those inconsistent multiple views to generate high quality 3D mesh and texture. We want to get a patch to the current multiple view diffusion scheme and hope that it can improve their final qualities. That's very simple and idea here. So the key challenge is that how to handle the inconsistency in the generated multiple view images. As shown below here, if you compare the image in the second row and third row is generated by the multiple view diffusion models. And for the input here, and also in the first row, we show the ground truth image of this shape, 3D shape, rendered from different views. You can say that actually it's different from this ground truth 3D shape views. And if you look at different views, their correspondence is not consistent. So it's difficult for us. I think there are some existing schemes. They try to add some disturbations and arguments there for the ground truth image so that it can train the model, hope that the model is robust to this inconsistent 3D views. But the result is not good. So what can we do? So during the experiment, actually our key observation is that when we check these multiple view diffusion models and generate the image there, we found that the very interesting thing is that the closer to the input view, the better generated image matches the training object, which means if you look at those views and compare to the ground truth multiple views there, their similarity is different. When the view is very close to the input view there, and the image is more consistent to the ground truth views. But when the view is far away from the input views, their generated image has more diversity, more variations, will be a little bit away from the ground truth views. So that gives us some hint that, so we designed a very simple, we call the view-dependent training scheme. The training scheme is very simple. It's like given a ground truth 3D shapes. We first use one ground truth view as the input. We generate multiple view diffusion, take the multiple view diffusion, generate multiple views here. So the network take this multiple input and try to get some 3D shape, and we render 3D shape use to the different views. And for the view that is very close to the ground truth view, we just use the ground truth depth image and normal image, and use L2 reconstruction error to do the loss functions. For all the other views, we know that it's not consistent to ground truth view. We just use the perception loss there. So it's a very simple idea, and we tried scheme, and it works quite well. And here we compare our result with ground truth and all the 3D models generated by other multiple view diffusion, plus some layer 3D reconstruction schemes, such as the news or other 3D reconstruction schemes. And you can see that our model generated better results and more close, similar to the ground truth there. And here, and we also try our model on the real internet images, and not in our training dataset, of course, and compare to other approaches for the single view 3D generation. I can say that our method generates a little bit better results. It keeps all the sharp features, generates a smooth result from the smooth surface there. Yeah. And another good thing is that we found that our models trained on 0, 1, 2, 3, plus, plus. But when we train, after training, we applied it to the multiple view image generated by all the other multiple view diffusion approach. It works quite well. We don't need any fine-tuning or other things. It works quite well. And we also say that our separate training scheme, our separate scheme that first generates 3D shapes, then using this view-dependent texture mapping schemes works quite well, and it's much better than you generate mesh and texture together using 3D reconstruction. We found that it's a better way to do that. And another thing we found that is that our model actually, after training, they only learn how to reconstruct the local details exactly. And when we give the views, it's not complete, and some views are missing, our model generation model is not good, which means they only focus on learning the how to reconstruct local details, and those multiple views will provide all the overall shape structures. That's our intention. It's good. In our cases, just since it's our intention, we don't want to learn any global shape structure. We only want to learn this how to reconstruct local details. So finally, compared to the text-to-image and video generators here, if you look at those multiple diffusion models, you can see that developing a 3D shape generator with high quality output and with good generality is still an open problem here. I think we are still not there, although we try a lot, we have a lot of efforts there. So I have introduced our effort in 3D learning field in the past years and what have I learned from these projects. So here I also want to share some lessons we have learned, and just for your reference. So the first thing we learned from all these projects is that we found that sometimes scaling up is more important than the algorithm or design some new algorithms or network structures. And when you design some method, I always ask myself is that if you have 10 times of data, whether we will follow the same way or design the same network structures. Sometimes you try to develop some new tricks, some improvements for network structure, introduce some new things there. But after you have more and more data, you'll find that it just wastes your time. When you scale up, the model becomes better, good. When you clean up your data, you have the good data, and it works very well. And in that way, we try to keep our design as simple as possible. Sometimes what you need to do might be some reduction, not the addition. You try to simplify your network, but not add more complexity to it. And try to figure out a way to scale the data up. Another thing we realize that we also feel difficult is that the system may be more important than a single algorithm. In the traditional SQL work, I have done many years SQL, we focus on algorithm design, right? We develop algorithms, it works, we try some small data, we test on a set of data, we publish the papers there. But when we try this deep learning works there, and all things contribute to the final performance of the algorithms, the data, the benchmark, the hyperparameters, all things contribute to that. And sometimes we focus too much on single algorithm, but we forgot about the whole system optimizations. We found that the progress is really, really slow, and sometimes when we fix some problem in the systems, the problem is not there, and the algorithm is overkilled, or something is lead to wrong directions. And another thing I learned here is that when we try to design some algorithm, try to start from your final model and data as you can. And we try to develop some algorithm based on some small number of data, but when we apply it to the large data or a different kind of data, a final data we want to test, we found that the algorithm totally failed. And all the things we learned from the previous model training doesn't work at all on the new data and the new models. So it's try to start from new final model and data as you can. Another thing we found that develop some numerical metric or good benchmark is more important than the visual inspections. When we want to try to develop a model, we want to try to say, for example, shape generations. We want to generate 500 models, shapes there, or something like that. It's so difficult for us to verify or validate whether this design works, is better than other designs. If we only say some small data examples, it always mislead us to wrong directions. We failed many, many times due to such things. And we found that the first thing, you try to develop some numerical metric. That will give you some numbers to compare, carefully compare the different approach. But definitely, you still need the visual inspections. But only based on the visual inspection, most likely will mislead you to some wrong things. And the last thing I learned lesson is that always data is so important things. When we try to clean up our data and try to fine-tune, really clean up our data, a lot of things works. The only thing is that you clean up your data and you retrain the model, do nothing. The result become much, much better. So, which means no dirty data work, no good results for many, many cases there. And I always tell my students to try to know more about the data, learn your network models. Before you play with data, try to learn more things about data, how the data distribution is, what the kind of data you have, what the typical data there. Try to learn more. That will be very, very helpful. Otherwise, you got the result, you know nothing. Yeah, that's something lessons that I learned from many, many failed projects and some successful projects I have done here. And looking forward, I think there are several things I want to say here. Just dump some out of my random thinking or shallow thinking or questions I have, and I have no answers, even have no ideas. I want to discuss with you and learn from you all about that. The first thing about the shape representations. And you can see that in all of my previous work I introduced here, we just use some rasterized representations like we call it point cloud, regular scenes. It's that raster representation, SDF scenes, people widely use in the 3D learning just because you can use the existing 2D vision framework for that, right? Just recently, there are some work based on the math structures triangle list. They developed some GPT scheme for shape generation or something like that. And you can think about how about if in someday we can record in the modeling software, we can record all the instructions artists used to model the 3D models. We can got all the instructions there. Then it means we got some code for each 3D models or each 3D synthetic scenes there. And we got all the collection of these instructions, whether we can leverage large language model to do this shape modeling task. It's just some coding task there, maybe. Yeah, I'm not sure. It's just some random thinking. And there are some good things and bad things about each representations. I'm not sure which one is good, but from this one, I learned that although people, for example, although people develop a really good scheme for the 3D shape generations, when you look at those 3D models generated there, although they look good, when you ask the artist, for example, game designer, they say, I will not use that, just because you broke all the mesh structures I have. I give you a good mesh, you give me some models, looks good, but you do the triangulation, everything is gone. I need to redesign the mesh topology on the mesh. So which means mesh structures just mean something for the graphics pipeline, graphics applications there. And another thing is that when we think about more and more about 3D understanding and generation, one thing is that I'm thinking more about whether 3D understanding and generation is just a special case of the image and video understanding or generation task there. When we have very, very powerful image and video generation or understanding framework or foundation models there, can we just regard some 3D as a multiple view images or videos there? And we can leverage the foundation models for the image video generation, then we solve all these 3D understanding and generation problems? I'm not sure. And if you look at this shape generations, right? People currently just use these multiple image generations. And think about it later, if we can generate this surrounding view videos in very good way, right? It's 3D consistent. Then the only thing you need to do might be is only 3D reconstruction, right? You got everything. And in this case, if the answer is yes or no, no matter what the answer is yes or no, what's the role of the limited 3D data or 3D learning layer? And the bad thing is that we think about the data. If we believe the data is the only thing we needed, and if you have the n amount of data n, you will have about 10 times or 100 times of the image and video data for that 3D scenes, right? So it seems that it's not good. But the 3D models always give us a lot of 3D prior there and may help us. I'm not sure what will happen, how to average or integrate this 3D prior or 3D learning with the 2D learning and put it together and get the benefit from this. I have no idea. Another thing is that we talk about some special questions or challenges in 3D learning. But I'm thinking about another thing is that what's a unique task in the 3D understanding and generation? And the vision guys, image guys, video guys will not do that. And one thing I'm not sure whether it's there is a 3D structure analysis. If you look at all the man-made shapes there, they have some very clear structures, and people can easily recognize it, and people use it to generate some new shapes, right? So whether those 3D structure analysis generation will be a unique task only in the 3D task there, I have no idea. But it's some thinking maybe we can find some unique but valuable tasks only for the 3D. Then we are there. Another thing is that from our view is that, I'm leading the graphics group in my company. Always the question people ask is that, do we still need 3D? What's the application of the 3D layer? Do we still need that, right? Why is it important in the future? So for the human visualization, for human eye, you can say that the image video generation models and disrupt the traditional approach, right? We still have the traditional approach there, but I think a lot of people will move to that new way to generate some image and videos there, right? But in that approach, in that field, 3D probably still a good way to control the image video generations, right? But may not the only way to generate the videos or other things, image there. And for 3D interactions, I think currently it's still important when we want to get these physically correct interactions in the games and for robotics there. We still need this way. Just interactions is very difficult for image and video generation to simulate or learn. But if you look at some recent progress about this end-to-end models that people trained to try to learn, it's called word models, other things there. And for the games and for the robotics there, and it seems that they can directly map the observations, even the 2D observations, to the final actions, and map the actions to some view changes or the content changes there. So if this model is still success and advanced, I think they may change this field, may also change this field. The only good thing is that I think about the fabrication and manufacturers. It's always there. We need a real 3D layer, and definitely that will be always needed for the 3D learning and the 3D representation, explicit 3D representations. And then I think about what are other applications for the 3D learning or our 3D representations. And recently I talked with some guys in the AI for science field. They are working on a lot of things, molecular things, neural things in the human brain, other things there. The real world is 3D, so beyond the human eye or human visions, there are a lot of things in the micro scales. They are the 3D. People need these real 3D representations so that they can analyze, they can learn the whole 3D structures or whole 3D things in the real world. That might be another applications for the 3D learning. That's some of my thinking. So finally, I would like to thank my group members, our interns, and many valuable discussions with other researchers and my colleagues there. And thank you for your attention. Yeah.
Thank you very much. So if you have questions, I hope you have many questions. There are mics over there, so please raise your hand, and the mic should be coming.
Thank you for the talk. So you kind of started with this guide of here's what NLP did, here's what vision did, and here's kind of we're sort of following those footsteps and how can we efficiently get to where they got. And I kind of want to ask a more philosophical question of, is there anything we also want to avoid in that way? Like, can we use the fact that we're going third to avoid some of the pitfalls of them, and how do those apply to 3D specifically?
Yeah, I think it's a really good question. I totally agree with you, Lad. I think a good direction is that since our 3D data is always limited, I think we should try to find other ways to use this limited data and still got some, how can I say, good models and with good generality and other capabilities there. I think it's a good chance to learn. One interesting thing I realized I'm really interested in is that we call the inverse procedural modeling, which means given 3D shape or other things, whether we can automatically learn what the procedure we create such models or other things. That will help us to maybe learn some rules there. Then we can, how can I say, extend those rules to generate other shapes or other things. I think that might be a good direction along that way I follow you mentioned there. Yeah, that's what I think. Yeah, thanks.
Yeah, okay, thanks for the talk. So on one hand, we see this trend, and you described it also, more data is always better.
Yeah.
Right? More data gives better results, and rather than improving the algorithms or the network, if you put more data into the network, in the end you get the better results. That's the one trend. On the other hand, you mentioned we need good data, clean data. Yeah? So we should be spending time on creating good data. And now I think this is the problem for 3D. Right?
Yeah.
Might not be difficult to get tons of bad 3D data. The difficult thing is getting tons of good 3D data. And I was wondering what you think we should do, right? Should we rather try with large amounts of bad 3D data and just take it and see how it works? Or should we focus more on trying to develop tools to process the bad data such that it becomes good data? Or I don't know, so something.
Yeah, I totally agree with you. I think if we look at the object world data, on one hand, we can say it's the first large-scale data we have. But if you really carefully check the data we have, 3D data we have now, I think the very good thing, I totally agree with you, is clean up the data first. so that we say how much good data we have. I think that's really, really critical for us to do that. We already started some effort to clean up the data layer. We hope that after we finish, we will release the data out. But I think it's more critical. But on the other hand, when we have this clean up data, I think we have the much more good data that will be also helpful. Yeah, it's both. But the current state, I agree with you. The good data, the amount of good data is really critical. Yeah, yeah, thanks. Yeah.
Thank you for your talk. At least for manufactured data, all manufacturers have perfect data available, right? But they won't make it accessible. If you take a car manufacturer, well, they have CAD models for every screw, and screw manufacturers have models for every screw. And the same, but nobody would share those data.
Yeah, that's. I agree with you. I think that for the 3D scenes, the difficulty here is that for a lot of shape data, they are, how can I say, some companies own it. They will not share those data out. And compared to the image data, all the people for the internet images, a lot of people capture the data there, so that you have so many data. So one possible way, I think, possibly is that if we can take those 2D image data we learn from that, combined with some kind of good 3D data, we hope that that will provide a good way for us to get a good, how can I say, the 3D understanding model or 3D generation models. So the idea here, I'm not sure whether it works, but my current thinking is that whether the 2D image can give you some coverage, the variation of all the 3D models or something like that, since I have a lot of data there. If you look at the, how can I say, it's a SDS-based Dream Fusion works there. They show that when you learn these so large image models there, the 3D prior is already there. That means they can distill the 3D models from those image diffusion models there. They have the good coverage and variations. But on the other hand, from the image, you can never learn some regular structures of the 3D shapes there. Right? It's the 3D shapes when you have the triangle mesh or chord mesh or curved surface there, we got these really vector representations there. So that we hope that we could learn some 3D prior about these vector representations from the relatively small amount of the 3D data, and we learn the distribution of the 3D models or 3D objects from the image data. But then the question is how to leverage both to gather good model for the 3D generation or 3D understanding or other tasks there. Yeah, I'm not sure, yeah. Oh,
At one point you said you don't want visual inspection if the quality is good, but is quality not defined kind of functional quality? Is the chair comfortable? Does it have dimensions which correspond to a human who wants to sit on it? Things like that. So it's not related to if is it nice, right? If you have the back of a chair should have a slope in the back and not in the front. These kind of things.
Yeah. So my point learned here is that since in traditional manual graphics applications, we cannot define some numerical metric that's really consistent to the human perceptions. So our convention is that we check every result using our human eye. We got our own judgment here. But on the other hand, and we found that although the numerical matrix is not good or sufficient to provide the final judgment about the qualities, it will give you some good, how can I say, is a statistics or some guideline to the overall quality of the generated results there. Since when you use the neural network deep learning, you got a lot of results, so many results there. You need to learn the result distributions or quality distributions there. You need some numerical results, numerical method to do some analysis. That is so important for us to develop the model and try to improve the models, especially when we have several possible solutions there. We don't know which one we should try. And that numerical metrics will be very, very helpful. That's based on our own experience. Yeah. But definitely we will combine with some visual check there. Yeah.
Hi, in one of your last slides, you mentioned the shape representations, and one of them was shape as modeling code. And has any work really been done in that field of trying to represent the shape as software procedures?
I haven't realized any work for the forward directions and use the code for the shape generation. That's some random thought I discussed with some people, but the bad thing is that we don't own any 3D modeling software and company, so we don't have such data. I think that maybe some software company has such data, or if you have an art school and the student may can collect a huge amount of data and try this, but currently we haven't. I know that the Daniel from the Brown University, Niloy, do a lot of good work to try to do the inverse precise given the shape. They try to learn some code structural segments there, and I'm not sure. I haven't checked their recent progress whether they use it also for the generation precise. Yeah.
I think there are some open source command line CAD systems that don't really have a GUI, so everything is done through procedures, and those might be useful.
Yeah, I think that might be useful. Actually, people try to use large language models, and they directly use large language models without fine-tuning and try to ask them to create some 3D models. And for simple 3D models, it works just because from their training data, I believe there are some simple algorithms or instructions to create some simple 3D shapes here. So they try an LL model, they found that for some simple objects or scene, it works. But definitely it's far away from the quality bar for our graphics people there. It's still very simple scenes. But I think given the lot of such data, probably it will work or worth to try. But as you mentioned, where to gather data is a big problem. Yeah.
And also just the representation of it, like in your example, you had the Stanford bunny,
Yep.
and you had a procedure, make left ear, make right ear. I mean, that can mean almost anything.
Oh, no, it's just some illustration, only
Right,
illustration
right.
purpose. Yeah.
But just designing perhaps the underlying graphics geometry system to base the procedures on, so you can then combine them in interesting ways, would be a project.
Mm.
Thank you.
Yeah, thanks.
Hi. Just a follow-up, I guess, on the question of 3D generative metrics, like FID. What have you settled on, like a favorite metric to use that you found was actually a useful guideline?
Sorry?
What's your favorite 3D generative metric?
Oh, actually, we use we call the image FID in our we developed in our experiment project here. We found it's quite useful for us to check the generated quality and diversity layer compared to other FID or how can I say the metrics layer. A very interesting thing is that we still use some numerical metrics people use for the 3D reconstructions to compare the shape quality or distance to layer. I think for reconstruction is okay just because we have this ground truth, right? But for generations, it may not be a good metric. For example, the chamfer distance or something like that, just because you will generate a set of shapes there, they will definitely different from the ground truth training data there. So compare is a chamfer distance or that may not give you good guidance. Although it might be a metric for you to measure some kind of quality later for your paper, but it will not give you some good guidance for the generation algorithm design or quality control there. Yeah. So we developed image FID. Currently, we found it's good, but definitely we will for the texture models, I think we still need some multiple view data, multiple view metrics there probably to check their consistency and the final quality there. Yeah.
Is there not a gap between the target distribution of images versus the rendered images you get from 3D generated?
Good question. I think will be. I would like to say will be have some gap there, but the good thing is that currently, if we look at the current two approach for the 3D generation, one we call the 3D aware generation. People use the GAN there, so the input will be image. When people train the GAN model, they still use the image. So the rendered image will be no different to the input ground truth real image. I like the way the image will be a good guidance. For other purpose, people, for the multiple view diffusion, people still use rendered 3D models as a base, how can I say, for the training purpose. So in that purpose, when you generate image, I think the image-based metric will still be a good metric. Not the perfect metric, but still good metric to give you some guidance there. Yeah.
Thank you.
Thank you. Yeah. Thank you.